So if I go to why it happened and search story insights for 11, which is November, I get this waterfall chart. Now if the chart's not labeled for you, you can again zoom out a little bit further. What this chart does is it breaks down the difference between November and my whole data set in the context of all of my variables. So the top bar here is the global average, 335 units. The bottom bar is the average for November, 803 units. This first green bar is the effect of November isolated from everything else. So Einstein Discovery estimates that the impact of November just by itself, when I remove the effect of different promotions and different product mixes and things of that nature, is 231 units. That tells me that November is in fact a good month for sales. The next several bars are all related to November. So I've asked for November, it told me the effect of November, then it's going to tell me some characteristics of November, then it's going to tell me some other things that are different about November that aren't necessarily characteristics of November. And all of those in combination will explain why November performs differently than the rest of my year. So the first characteristic of November is how coupons perform in November. The impact here is 71 units. And if I look at the description on the left, it says promotion as coupon occurs about 8% of the time globally, but changes to about 24% when it's known that date is November. And because of these cases, daily quantity increases by about 71 units. So coupons generally perform well. We'll see that in the rest of the story. But they perform particularly well in November. That's what this bar is calling out. Coupons work really well in November, and we're doing them a lot, and that's driving up the average by 71 units. Similarly, display promotions in November specifically are having an impact of 63 units. Here's the impact of 10% discounts in November. And San Francisco also performing particularly well in November drives up the average. This next bar is the combination of 25 terms subtracting 87 units off the average. Now, a thing to note is while this bar looks large, because it's 87, which is larger than any of these terms, it's 25 terms combined. Einstein Discovery is about getting you to meaningful insights quickly, so it calls out the biggest effects first, and then it puts the rest of them into this single bar here, because they have to be represented somewhere. So keep in mind that none of the 25 terms in here are larger than the ones we've shown you. There's just a lot of them being combined. The next bar we see is promotion as mail-in. Now, as I said before, mail-in rebates don't tend to be well received by customers. So it's surprising that the impact here is positive. You can see the impact is plus 40 units. If we look at the description, though, we see promotion as mail-in occurs 57% of the time globally, but changes to about 9% when it's known that date is November. Because of these cases, daily quantity increases by 40 units. So Einstein Discovery actually picked up on the fact that mail-ins don't work that well. You can actually see in this tooltip that the coefficient is negative. That means that the model has learned that mail-ins reduce sales. But because we're doing a bad thing less often, that's having a positive impact on the month of November. The way to interpret these bars is there are good things and bad things in your business, and things can happen more or less often. So this chart reveals to you if you're doing a good thing more often, a good thing less often, a bad thing more often, or a bad thing less often. In this case, promotion as mail-in in November is a case where we're doing a bad thing less often, and it's having a positive impact on our business. You'll see there are also bars for San Francisco doing mail-in promotions, display promotions by themselves, and coupons. Note that display and coupon here are global effects. Generally speaking, displays and coupons perform well, but in November they perform particularly well, which is why they're called out separately over here. The last bar you'll see is an unexplained bar. The interesting thing about these charts is that it starts with observed reality at the top, it ends with observed reality in the bottom, and it provides you a statistical representation of what's going on in your data in the middle. And sometimes that statistical representation won't match up exactly with reality. And in fact, it shouldn't. If it did, it would do what we call overfitting, which I'll speak about momentarily. But because the statistical representation doesn't line up perfect with reality, we have to account for that difference somewhere, and we call that unexplained. So now we understand why November looks so good. It's largely because it is largely that November is just a good month for sales, but it's also because we're doing different promotion behavior in the month of November, and that's driving up its average. If we go back to the chart we were looking at before, the date variable, I do find it interesting that we peak at November and that sales in December are actually lower. Einstein Discovery can also help us understand what's going on there. Why is December lower than November? For that, I'm going to ask, what's the difference? I'm going to ask for the difference between the month of 11 and 12. So just like the why it happened chart, this is going to provide a waterfall that explains the difference between November and December. You can see in the description that key differences between the months are how promotion is coupon and promotion is display work in November. In both cases, December performs worse. You'll see this unlabeled bar here of minus 67 units. You'll see this unlabeled bar here for minus 67 units. That's the difference between December and November, independent of everything else. So December is lower than November largely because of how coupons and display promotions work, but also because sales in December just also tend to be lower than November. If you do A/B testing in your business and ask for the difference between the treatment and the control, this bar would reflect the difference of the treatment independent of all the other differences between your samples. To be able to do this kind of analysis requires a regression model. Now, if you took statistics, you're probably thinking, regression model, isn't that kind of basic? We did linear regression back when I was an undergrad. Ordinary least squares regression is what you probably learned in your statistics course, but it's actually not well suited for the kind of modeling we need, and it's actually not possible to perform ordinary least squares on the data sets we create, so it's not what Einstein discovery does. We do linear regression, or logistic if you select a binary outcome, but it's actually piecewise linear or logistic ridge regression with interaction terms. So now we should talk about what a ridge regression model is and what are its benefits. So if I start with my data points here, I have 10 data points and some clear relationship between my x variable and my y variable. Now what old-fashioned statistical modeling would do is it would cut this 10 data points into a training set and a test set. I would train the model on the training set and test it on the test set, and I draw my conclusions from there. So for ease, I'm just going to cut it in half. I'm going to use the green points to build the model and the red points to test my model. Now if I go sufficiently overboard with my model, it is very easy for me to hit every green point exactly. It's not difficult to build a model that hits every training data point perfectly. And it doesn't appear that this model performs that badly because the red points aren't that far from the line. However, what you have to remember is what we care about is vertical distances. So these are my actual errors. Note that these are squares mathematically, but because my axes are stretched, they appear to be rectangles. So this red point here, even though it's close to the line here, it's actually off by this much. That's a pretty large error. You'll see the sum of the squared errors in this case is 235. So a hallmark of what we call overfitting is if I build a model that fits my training data really well, and in fact I had 0 sum of squared errors on my training data, but it doesn't fit my validation data very well. In this case, my sum of squared errors was 235 units. Another indicator of what we call overfitting is the coefficients. If you look at the scale of my outcome variable, all of my observations are between about minus 7.5 and plus 5 point something. But if I look at my coefficients, I see minus 32.5, minus 39, 17.9, and 19.1. This would be like if you came to me and asked how well our marketing campaign worked, and I said customers that were in the campaign were worth $999,990 more, and then we subtract off $10 for state as Illinois. And you would just say, well, why didn't you just tell me that it adds $10 for customers in Illinois? It's just a really roundabout way of doing that. That's what this model is doing. It's going to extreme lengths to hit those green points perfectly at the cost of making good predictions. Overfitting can be thought of as the model memorizing data points, not learning trends in the data. And that's what this model is doing. But because large coefficients alert us to this overfitting condition, we can use that for our benefit. What we're going to do is play a game of whack-a-mole with these coefficients. Each variable that I provide this model can be thought of as a mole. Stronger moles are variables that provide good signal. Weaker moles are moles that provide bad signal, or what we would call noise in statistical modeling. Don't worry, here at Salesforce, we love our woodland creatures. No moles are harmed in the making of this demonstration. So here we have our overfit model. You could see our sum of squared errors, 235. You could see our coefficients here. This is our ordinary least squares model. What I have control over is the size of the hammer that I hit these moles with. If I hit them with a small hammer, it has a small impact on the coefficients, but you can see the sum of the squared errors is reduced drastically already. As I hit them with progressively larger hammers, you'll see the coefficients shrink to the scale of my data pretty quickly, and so does the sum of the squared errors. So I could try different hammer weights, but there's a problem. If I hit them with Mjolnir, none of the moles are worthy. You'll see all of the coefficients go down to 0. This would be called underfitting. So there's some happy medium. There's some hammer weight that allows good moles, or good predictors, to actually carry weight and pushes our bad moles down to nothing where they won't have a bad effect. So that's what we have to find. So if I plot my sum of squared errors against my lambda values, you can see there's a minimum somewhere around here. There is a lambda value that produces the best predictions. If I zoom in, I can see that it's about 0.844. So if I go back and build a model using a lambda of 0.844, I get this line, and it looks pretty good. There's still a problem, though. What if I had taken the red data points and fit the model on there and tested it on the green data points? Using that same lambda, the model still looks pretty good. Sum of the squared errors is 14.22. But keep in mind, we said this lambda produced the best predictions. Why then do my sum of the squared errors decrease if I use larger lambda values? That's because on the first cut of the data, that was my best lambda, but that's not necessarily the best lambda on this cut of the data. So that's the problem with the old-fashioned approach to statistical modeling, where you just take one validation set. Depending on which validation set you take and which training set you're left with, you might end up with a different model that performs best. That's obviously not ideal for business purposes. So to rectify this, we'll look at lambda on both halves of the data. The blue line represents the fit of the first half, the green line represents the fit of the second half. If I zoom in, you'll see they have different minimums. Now, I don't want a model that works best on the first half of the data. I don't want a model that works best on the second half of the data. I want a model that works best on average. So what I'm going to do is I'm going to combine these two and find the minimum of that. In this case, 1.9. Minimum's around here. So then I can go back and take all of my data points, use a lambda value of 1.9 and fit a final model. This allows me to use all of my data points to train my model, which means that creating a validation set is not depriving my model of knowledge. And it also guarantees that it'll provide good predictions because that's how I chose lambda. I chose the lambda value that provided the best predictions on average. Another benefit of this is fit statistics. If I were to just calculate the errors on this line, I'd say the mean squared error is 1.58. But all of these data points were used to train this model, so this is an optimistic estimate of my mean squared error. But if I look at how well it fit on the two halves of the data I created, I see the mean squared error is actually 2.68. That's a better estimate of how this model will work in the real world. What you've seen me demonstrate here is called twofold validation. Einstein Discovery actually does fourfold validation, where we take 25% cuts of the data for our validation sets, we fit models across the four, and that guarantees that our models will not overfit and that our error estimates will reflect reality. So now that we understand that we have a regression model here, we can also start using it for predictions. So if I click the menu here and ask for predictions and improvements, I can specify a scenario that I want a prediction for. So I'm currently filming this in April, so I'm going to do a prediction for a campaign in May. I'm in San Francisco. I'm going to sell some scarves, because we are in San Francisco after all. I was going to do a mail-in because I didn't know any better, and it was going to be worth 10%. So the prediction for this campaign is 806 units. It's telling me if I run a campaign in May in San Francisco with a 10% mail-in on scarves, I'll sell about 806 or 807 of them. What we found is if you just give someone a prediction, though, if they don't know where it came from, they're not likely to trust it. So this waterfall chart exists for us to be able to validate the prediction that we're getting. So starting with this red bar, it tells me when I do mail-ins in San Francisco, that tends to hurt my sales by about 294 units. Sales in May in San Francisco are actually lower by 126 units. Sales in May in San Francisco tend to be lower. Doing 10% discounts in May tends to hurt me. Mail-ins by themselves also reduces sales. What's helping this prediction is selling scarves in San Francisco, which makes perfect sense if you think about it. And the fact that we're doing this promotion in San Francisco, which we saw earlier is one of our best performing cities. So you can step through these insights and validate each one of them. We know that mail-ins don't tend to work well, and we know that San Francisco is one of our top performing cities. So because of this chart, I can trust that this prediction makes sense. But we can also go further. Now that we see that mail-ins are actually hurting us a little bit, we can ask Einstein Discovery, well, which promotion should we run? So if I tell it that I can change promotion and scroll to the second chart, here's my prediction for my mail-ins, my 806 units. It tells me if I do a display promotion, I'd actually sell about 1,765, and if I do a coupon, I do about 1,780. So this is how you can use Einstein Discovery to get a prediction and improve upon that prediction with a prescription. This bar here represents the baseline. In previous waterfall charts, we saw that this was either the global average or this was some other subgroup. Baseline, however, is neither of those things. It's actually the intercept of the model. So to explain why you don't need to focus on this, let's go back into Python. Suppose I have this data with age and salary. If I fit a line to this data set, I end up with a line that looks like this, and my intercept all the way over here. In this use case, the intercept is actually $23,697. The practical interpretation of this intercept in the context of this problem is that when you're born, you're making $23,697. Now, I'm pretty sure that I don't live in Norway, so this probably isn't true. And in fact, I think in the US, when you're born, you already have student loans. So clearly, this doesn't represent reality. The reason is all of my data is over here, so my model works over here and a little bit beyond. It does not work all the way over here. The only value of the intercept in a statistical model like this is to ensure that the predictions are unbiased, meaning that the average error is 0. That's the only purpose they serve, and that's the only reason the baseline exists. So don't dwell on this bar. Now, a final thing I should say, it's a common misconception that linear regression only handles lines. And obviously your business is probably a lot more complex than just lines. Some data scientists will occasionally spend time trying to find the most appropriate complex relationship between your input variables and your output variable. And if you think of all the possibilities, it makes sense why it can take a lot of time. There's quadratic relationships, cubic relationships, various exponential relationships, logarithmic relationships, squared root, cubed root, fourth root, all possible combinations of them as well. But Einstein Discovery wants to provide a good model quickly so you can start optimizing your business now. So we actually take a page out of the Flat Earth Society's playbook. So some of our NBA superstars and lots of other people in my generation, unfortunately, look around and they say, yeah, I look around where I live and everything seems flat. The problem, obviously, is that they're looking too close. If you start to zoom out a little bit, or take a spaceship, you start to realize that, no, what we live on is actually spherical. So Einstein Discovery does something similar. We take what we call a piecewise approach. To demonstrate the value of this, I'll show you my data. So I'm a quantified self-nerd, so this is actually data from my house. The x-axis is the low temperature where I live in Chicago. The y-axis is how many kilowatt hours of electricity I use. If I just use the average for all my predictions, I get an RMSE of 8.8. RMSE is root mean squared error. So I'm taking my errors, squaring them like I told you we have to, taking the average of that, and taking the square root to undo the fact that I squared them here. This is basically the standard deviation of my errors, and I want this to be small. I want all of my errors to be compact around 0, not spread out. So this is my baseline. If I just do simple linear regression, I end up with an RMSE of 7.45, but you can see this line doesn't fit very well. It underpredicts towards the left, it overpredicts for temperatures around 50 degrees, and then it underpredicts again for temperatures near 70. However, I know there's a season where I use air conditioning and there's a season where I don't, and the season splits right around a low temperature for the day around 50 degrees. So if I build a two-part piecewise model, I end up with an RMSE of 5.37. Einstein Discovery obviously wouldn't know to make this cut at 50 degrees. So what it does by default is it deciles the low temperature. And keep in mind that the models that Einstein Discovery builds contain many variables, and I'm limited here to showing you an example with one variable. But if Einstein Discovery were to build a model with one variable, it would look something like this. And you can see here the RMSE is 5.40. So here I had 5.37 with intimate knowledge of the subject. And here's Einstein Discovery getting 5.4 without even thinking about it. So you can see our piecewise approach actually works pretty well. So final point. We've looked through the Einstein Discovery story. We've spent time on each chart so you understand what they're telling you. Why should you spend time reviewing the story? Einstein Discovery is a machine. It knows math. You know your business. When you apply machine learning to a data set, It's actually possible that the machine learns things that you didn't intend it to learn. Reviewing the story is how you communicate with Einstein Discovery to identify whether the machine has learned what it should have learned. If you see counterintuitive insights, either the data is causing issues, in which case, is there a way to bring in more data that can resolve it, or should we remove some variables that are causing problems? Or, because we're humans, we should accept that maybe we're just wrong. But either way, you should investigate these issues to get to a story that's cohesive and understands the patterns in your business. And that's why you should spend time iterating through an analysis before settling on one that you make business decisions using.